Welcome to this educational game I've created for you. Today, I invite you to experience quality control differently. Through play, you'll step into the role of a laboratory, face real results, make critical decisions, and sometimes spot errors. Are you ready to take on the challenge? Will you be able to recognize the warning signs before it's too late? And most importantly, can you avoid repeating unnecessary controls and delaying patient results? Before we start playing, let's take a moment to remember what internal quality control is really for. Its goal is to mimic, as closely as possible, the variability we see in real patient samples. It's great at detecting persistent errors, like a shift or too much scatter, measured by bias or coefficient of variation. But be careful. It's often powerless against one-off issues, the so-called flying errors that slip under the radar. This game has a double mission: educational and fun. Educational because it lets you simulate analytical variability, spot bias or abnormal dispersion, and understand how that can affect a medical decision. Fun because you'll play with results, test different QC rules, and train as if you were in a real-world situation. All of it follows a Six Sigma-inspired logic, but made simple and visual. To start, divide yourselves into 5 groups. Each group will receive a deck of cards representing results expressed as percentage deviations from a target value. Lay the cards out in front of you. They represent the distribution of results from your analytical method. The values are deliberately rounded and simplified, so you can focus on the reasoning, not the decimals. The goal isn't to simulate a real assay, but to understand how drift happens. You might be wondering how the deviations were calculated. Let's take a real example. A lab measured potassium at 6.00 millimoles per litre, while the target value was 5.96. The difference is plus 0.04 millimoles per litre, which is plus 0.7%. In our game, we round that to plus 1% and represent it with a plus 1% card. This is how all the cards work. Compare the result to the target, calculate the percentage deviation, round it, and that becomes your card. We're going to apply this calculation to 36 cards, as if each card represented a potassium result. For each value, we compare the result to the target value, calculate the percentage deviation, then round it. This rounded percentage is what you'll see on the cards. It's a simplified way to support interpretation. When I talk about a target value for internal quality control, I'm referring to the average observed across a group of comparable laboratories. It's the same principle used in external quality assessment programs. We assume this average is the best possible estimate of the true target value. We've now applied this calculation to a full set of simulated results and created a deck of 36 cards. Each card represents a result expressed as a percentage deviation from its target. This collection will allow us to simulate different analytical methods with varying levels of variability. We've now applied this calculation to a full set of simulated results and created a deck of 36 cards. Each card represents a result expressed as a percentage deviation from its target. This collection will allow us to simulate different analytical methods with varying levels of variability. Each group sorts its cards. Start by laying them out, then sort them to visualize the distribution of your results. The green group will likely observe a tighter distribution, while the red group will see more spread. This reflects different performance levels of the analytical methods. This game is based on a Gaussian distribution. The cards were drawn following a normal distribution. This makes it possible to simulate a realistic scenario where results naturally vary around a mean. You'll see that even with a high-performing method, some cards deviate significantly from the target. And learning to detect those is exactly the point of this exercise. Let's go back to our three method groups. The distribution of the cards in each group follows a Gaussian curve. That means most results are concentrated around the target value, and the further you move away from it, the rarer the results become. This is known as the 68.95.997 rule. About 68% of results lie within plus or minus 1 standard deviation, 95% within plus or minus 2, and 99.7% within plus or minus 3 standard deviations, 99.7% within plus or minus 3. In our 36-card game, this means you'll typically find 25 cards within the plus or minus 1 sigma range, 10 cards between plus or minus 1 and plus 2, minus 1 or 2 cards in the extreme zones. These proportions make the game realistic for a well-calibrated method. But beware. As soon as an error appears, the distribution shifts subtly. Why do we talk about Six Sigma? Because a Six Sigma method is so precise that it would produce fewer than 2 errors per billion observations outside the plus or minus 6 sigma range. In other words, if you draw a card showing more than plus 6% or less than minus 6%, you most likely have a real analytical issue. Let's take a concrete example. At the Quality Control Center in Zurich, any deviation greater than plus 6% or less than minus 6% from the target is considered unacceptable. This exceeds the allowed tolerance for potassium. Such a result is therefore incorrect, as it could lead to a wrong clinical decision, misdiagnosis, inappropriate treatment, or misleading follow-up. Remember the 3 groups of cards you received. The green group represents a very stable method, with cards ranging from minus 2% to plus 3%. The yellow group is slightly more variable, from minus 4% to plus 4%. And the red group simulates a less precise method, from negative 8% to plus 7%, with 3 cards outside the acceptable range. These are the cards you need to identify. They represent critical results that could lead to a medical error. Now, I can introduce the concept of Six Sigma. A Six Sigma method is one whose results stay well within the acceptable limits, which, for potassium, range from plus 6% to minus 6%. According to probability laws, you would need to draw 1 billion cards to get just 2 outside those plus 6% or minus 6% limits. The 3 sigma method is the minimum we accept for our methods. The deviations begin to approach the limits, but normally they rarely exceed them. And then there's the 2 sigma method. That's the one we fear. With this level of performance, results frequently fall outside the plus or minus 6% limits. In our game, that's equivalent to 3 cards out of 36. So a method with less than 3 sigma cannot be accepted. How does the game work? The Game Master starts with the green deck. They ask the player 2 questions. How many quality controls would you like to perform? How many patients will you analyze between 2 controls? Then, without warning, at 2 key moments during the game, the Game Master will discreetly switch decks to simulate an incident, first using the yellow deck, then the red one. They may also switch back to simulate a system repair. For those familiar with control charts or Levy-Jennings charts, this is equivalent to a drift over time. By drawing first from the green deck, then yellow, then red, the Game Master introduces instability into the system. Your role: detect the moment when the method starts to drift. Your mission as a player is to stay alert. Observe trends, take note of deviations, and try to detect the exact moment I change the deck. If in doubt, you may ask for an extra control card to confirm your suspicion. At the end, all the cards will be revealed, and you'll see whether you were too cautious or too late. At the end of the game, we'll do a short debrief. When did you detect the deck change? How many erroneous results were introduced? Did your strategy lead to false rejections? Or, on the contrary, to a failure to detect errors? And most importantly, what could you adjust to improve your performance without rejecting valid series unnecessarily? We start with a Six Sigma method, which in this case is a potassium test. That's the green deck. I decide to perform 2 quality controls, which look perfectly fine, and then I move on to testing patients. We don't know the exact error in the patient's results, but we assume that's the whole point of a control, that it's similar to what we see in the control samples. I perform my second control after the series. This may represent 50 patients, although I've used only 5 cards because my deck has only 36 cards. Then I run 50 more patient samples. I do another control, and I believe I'm still using a Six Sigma method. So I'm happy. I continue with more patients thinking everything's still fine. I don't notice any incident that may have occurred. And now, thanks to the magic of the game, I can discover what the actual errors were in my patient results. These are the patient cards I hadn't seen before, the deviations applied to those results. And you can see that for all my patients, I got results that were very close to the true value, even though in real life, we never know the true value of a patient's sample. Now the real game begins. At first, I'll draw controls from the green deck, but from now on, I can switch at any moment to the orange deck, and then to the red one. It's up to you to detect an incident. Since my morning controls look fine, I go ahead with my patient samples. That covers 50 patients. I do a control at the end of the series. Still looks good. I decide to continue with another 50 patients. Then, another control. Still excellent. No problem in sight. For those who are paying close attention, there's a +4 card here. That doesn't belong in the green deck. So maybe we're now in the orange deck. We can choose to troubleshoot and try to go back to green, or decide it's not a serious error yet, since it doesn't exceed 4%, which is 2/3 of the total allowable error. So I may decide to carry on. I process my patient samples. And actually, I go back to the green deck. If I had briefly dipped into orange, I now believe I'm back on track. I do another control, +2%. Looks fine, totally acceptable. I go on with my patient series, then a final control to close the series. Everything seems fine. I didn't feel there was a deck switch, or maybe just around here, but it looked like the system recovered. And now, thanks to the magic of the game, we reveal what the patient cards really were. We can see there was a first incident here, where I increased the CV. I switched from green to orange but didn't notice for that patient series. Then I noticed, but chose to continue because I felt it wasn't significant. But then, the incident worsened right after this control. The CV increased again. I didn't realize it happened at the start of my patient series. So I released those patient results. Here we see a +8% result. That's a lab error. And the +7% too. So in the end, I didn't detect anything that actually happened. And there it is. The incident happened. You didn't know it yet, but 2 erroneous cards were drawn. They exceeded the allowable limits, but you hadn't detected them. This is exactly what sometimes happens in real life. An error slips into the results and goes unnoticed. Now let's move on to another card game. You can already see that the first group is drawing cards ranging from -8% to +5%. If this were a potassium test, those would be bad cards. The second group, however, has cards going up to +15%, and the lowest card is +3%. There are no more negative deviations. The last group shows results going as high as +19%. These represent the results of an LDL cholesterol test, where the QUALB allows a tolerance of plus or minus 18%. You can see that the method with the -8% card is the 6 sigma method. Since this result is still far from the total allowable error, more than half of the QUALB tolerance. The 3 sigma method here is the one with the worst result at +15%. That's already close to the plus or -18% limit. And finally, our 2 sigma method is the one with an error card at +19%. What happened? We still have a nice Gaussian curve, just like for potassium, but there's something new here. The shape of the Gaussian curve stays the same, but it has shifted to the right. All values are now higher. That's what we call a bias. And for the 2 sigma method, the shape of the curve is still the same, but the bias is even greater. So if your method has a bias, it will reduce the sigma. Even with a very good coefficient of variation, if there's bias, you can fall down to 2 sigma, which makes the method unacceptable. You need to remember that the QUALB tolerance depends on the type of analysis performed. It can range from plus or -6% for potassium to plus or -18% for LDL cholesterol, and even up to plus or -24% for troponin. You can find all the detailed requirements on the QUALB website. On the Westgard website, you will find different sources of tolerance, known as total allowable error, or, more recently, analytical performance specifications. As you can see here, for potassium, depending on the country, Germany, Rilliback, Brazil, China, Australia, RCPA, Spain, or based on biological variation, there are different sources for total allowable error. Each laboratory must ultimately choose its own total allowable error, depending on its context, since there is no global consensus. Now we're playing with LDL. We'll apply the QUALB strategy, which states that, if the result exceeds the total allowable error, plus or -18%, it's a rejection. If it exceeds 2/3 of the total allowable error, plus or -12% once, it's an alert. If it exceeds 2/3 twice, it's a rejection. We begin the morning with our control, starting with the 6 sigma method. My controls are +4% and +4%. I decide it's okay to proceed. I process my 50 patients. Then, -1%. I'm still happy, all good. +11%. I'm approaching the alert level but still acceptable. +13%. Now I've crossed the alert level. That's 1 alert. What do? I troubleshoot and then retest. Now my control is fine. The issue is solved. I do another control to be sure. All good. I continue. +9%, fine. +5%, also fine. Then +11%. Okay, still within limits. I proceed with my patients. Oops, +16%. That's not catastrophic, but it's 1 time over 2/3 of T. I repeat the control, again over 2/3. 2 alerts equals 1 rejection. I must troubleshoot. I suspect a bias of more than +16%. I recalibrate the method. Now I get +7%. Problem solved. I go on with my patients. +8%, still good. And that's the end of my day. So what do we see at the end? Where did the incidents occur? Here, a bias was introduced, raising values, but it's still within a 3 sigma method, moderate error. Then, increasing deviations, and I thought I'd fixed it with calibration, but I was still within a 3 sigma method. Later, I didn't detect any issue, but I had inserted a serious bias. I had switched to a 2 sigma method without noticing. I continued testing patients. Finally, I realized something was wrong, thought I fixed it again. But at plus 19%, I had generated a diagnostic or treatment error for my patient and never even noticed. What's the takeaway from this round? Well, with this strategy, I couldn't prevent errors. Maybe I realized, with that card, that I had switched decks. But since the rule says one card beyond 2/3 of the T is just an alert, I didn't necessarily stop. Or maybe I did stop and took action. But I wrongly believed the problem was fixed based on the following cards. Then, when the second incident occurred, I was unlucky. The cards just before and after were fine, so I validated my patients. After that, I got unlucky again. I didn't draw the plus 19% card. Had it shown up during a control, I would have noticed I'd switched to the 2 sigma deck. But I didn't draw it, and didn't notice the drop in method performance. Here you can see the results again, now with the lines at plus or minus 12%. That's 2/3 of the total allowable error. And plus or minus 18%, the Qualab tolerance for LDL. The 6 sigma zone lies well below this. Variations stay within half the allowable error. The 3 sigma method starts to flirt with the 12% threshold, and the 2 sigma method has results exceeding plus or minus 18%, though not all of them. Let's replay the game with the same decks. We'll also start with the 6 sigma method, but this time we'll apply a strategy based on the real mean and standard deviations. The rule is, if we exceed plus or minus 6% twice, that's a rejection. Or if we exceed plus or minus 9% once, i.e. 3 standard deviations, that's also a rejection. So, we begin with our controls. They look good. I can go ahead with my patient series. Then I check again. Still all good. I'm clearly in a 6 sigma situation, so I proceed with my patients. Now, plus 11%. That's above 9%, so it's a rejection. I troubleshoot, but I can't fix it. I try again. Still no solution. Eventually, I recalibrate and it works. I double-check. Looks fine. So now I can release my patient results. I check a third time to be sure. Then again. And, oops. Another error. Plus 13%. That's a rejection, so I troubleshoot. This time it works. I get plus 6%, within limits. I double-check, but wait, this is still above 6%. Let's repeat to be sure. This time I get plus 2% twice, so that's a rejection. More troubleshooting. It works again. Plus 5%. I continue my testing. Then plus 7% once and twice. So that's 2 times over 2 standard deviations, which means rejection. And now I get a result above 3 standard deviations. Another rejection. I try to troubleshoot again, but I can't fix it. Another result shows 2 times above 2 standard deviations, still unacceptable. I troubleshoot again, no luck. Eventually, I hit a result beyond the total allowable error of 18% for LDL. I call in the technician, still no fix. At this point, it's over. We realize we've dropped into a 2 sigma performance, and we stop. This time, we've successfully detected the analytical error. At first, we missed it. It was within the patient series. But when we transitioned into the 3 sigma method, we got blocked. Then we were tricked by good cards, so we continued. But it was still 3 sigma. Later, the error popped up mid-series again. We missed it initially, but eventually caught it and stopped. So in the end, what happened? When we were using the 6 sigma method, no rules were violated. But when we dropped to the 3 sigma method, many rules were violated. There may have been a few false rejections, since a 3 sigma method could still be considered acceptable. but we saw that it was fairly restrictive. However, the error detection rate was excellent because our system detected the issue here, with the infamous plus 19%, which fortunately was not assigned to a patient. The visual representation here is slightly different. For a Six Sigma method, the plus or minus 3 standard deviation limits lie at half the total allowable error, TEA. That's the very definition of a Six Sigma method, when there's no bias. Then, when we move to the 3 Sigma method, you can see that almost all results triggered alarms or rejections. So in terms of error detection, it works very well, but it also generates false rejections. In summary, an excellent error detection rate, but at the cost of heavier workload. So here we are. With this game, you experienced firsthand what can happen when an analytical system starts to drift. Sometimes it was surprising, sometimes frustrating, just like in real lab life. You had to make decisions, observe, interpret results, without always knowing what was happening behind the scenes. That's exactly what we face every day in technical or clinical validation. Now that you've had this hands-on experience, let's take a step back. Let's ask the right questions. What quality control strategies reliably detect errors without triggering too many false positives? And most importantly, how do you choose the right rule based on your method's performance? That's what we'll explore together in the second part. In May 2009, I had the chance to attend the Bio-Rad International Conference in Sitges, Spain. That meeting with Dr. James Westgard was a turning point. It inspired me to explore his work further and discover the Six Sigma approach in laboratory medicine through his website and publications. Since then, I've been passionate about sharing this approach with others. And this game is one of my attempts. Special thanks to Bio-Rad and to Laurent Kupiecki for capturing this moment in Sitges.